Okay. Well, last week we talked about regression and basically talked about various ways how that it affects complexity of a model, how models can be made nonlinear and stuff like that. We'll quickly go over them again. And then we also talked about regularized regression, and today we'll talk about Bayesian regression, which again can be basically be viewed as a regularized form of regression, or many regularized forms of regression can be viewed as can be given a Bayesian interpretation. Then I want to go back a little bit to the genome-wide association studies and just on a very high level discuss about ways how these Bayesian methods could be used for GWAS or for statistical tests in general. Okay, so well, we said basically in a regression we always have to estimate some parameters, so there's obviously some uncertainty. And the other thing is, we said that by introducing these sorts of basis functions we can make the function nonlinear. Right, I put the link to these Gaussian identities online. The Bishop book is sadly not freely available online. Put at least a link to the Tipshirani and Hasty book, Elements of Statistical Learning online. It also covers a lot of these things, but it's a little bit more broader, and also puts a lot of focus on the lasso and these kind of things that Tipshirani has worked on. But also has a good introduction and a little bit of different view as what I present here on the same things. Okay, so well, we said that for the function with Gaussian noise, this gives us a likelihood, and well, linear regression is this linear function. Well, Gaussian likelihood corresponds to squared sum of squares minimization, and can get the maximum likelihood estimate, which is, as we said, unregularized. Now, in order to make that nonlinear, we can introduce these basis functions. So the idea with these basis functions was that we take the original input x and we put it into a function, which is possibly nonlinear. And we don't use just one function, for example, but many functions. And we can now add, basically, create a new linear classifier or a new linear function in these individual basis functions of x. And what this gives us is a nonlinear function. For example, these functions could be polynomials, but in principle they can be everything. I mean, it really depends on what you think your data looks like, what's your dependence between x and y, and that is kind of what you would use to choose these functions. For example, if you choose these Gaussian basis functions, then one thing that will happen is that the functions that you get out of it, the regression functions, will be very smooth. Or sigmoidal functions, actually they create an output very similar to these RBFs. And well, if we start with the polynomial, I mean, we discussed that there is a dependence on the number of these basis functions that we use. So the number of parameters influence the complexity of the model, and say we generate data here from a sinus function here plus Gaussian noise. These are the blue points, and then we fit polynomial of degree 0. Then we just get the mean of those. While if we increase the degree of the polynomial, we get more complicated function. But in the beginning, we see that probably the models are too little complex in order to describe this nonlinear function. At some point for a degree of 3, they match it quite well. But if we increase the polynomial too much, if we increase the number of parameters, the number of basis functions, then we get kind of, I mean, a perfect fit to our data, but the functions that we get out of it are kind of unrealistic and a little bit ridiculous in this sense. And one way to describe this like degree of ridiculousness is basically by the variance in the regression coefficients, where we see that the variance goes up dramatically. We get these regression coefficients here that are, those are larger than 1 million in the absolute value. And the assumption is that if we want to use them, then probably they have very bad extrapolation performance. So if you want to actually learn the true function. So generalization performance, yeah?
Why there are some negative values?
Yeah, because I mean we're fitting these beta weights that we fit, the maximum likelihood beta weights. They can be positive or negative. They are basically you can, for example, if you think of the SNP as a feature, and the height is the target variable that you're regressing on, you can have a mutation that makes you a little bit taller or a little bit smaller. So it can be positive or negative. And in order to measure this generalization performance, we said that we can measure the rooted mean squared error on new data. Instead of the training data, we go to new data. And then if we do that and plot it as a function of the order of the polynomial, we see that the rooted mean squared error in the beginning tracks between train and test. It's quite similar. There's always a little gap. So on train, the rooted mean squared error is always a little bit low. But then there is always this point where we perfectly fit the training data, and that is usually where we will perform very badly, very poorly on the test data, and that is overfitting, where this part here, where we don't get, where we both on the training and on the test data get very poor performances, what we call underfitting. So this is the region where the function has too little complexity, and here's where it has too large complexity, basically. And yeah, we said there are various ways to avoid overfitting. So for a given function of a fixed complexity, like here, maximum likelihood estimation with the order 9 polynomial, we said that the number of training points is a way to get good estimates of these parameters, even though on small data set sizes, on large data set sizes, we actually get quite a good fit. So the number of training points regularizes the function. Well, this is important for, on the one side, for these basis function regressions, but also if we have just a normal linear regressor on a very high dimensional data set. Well, if we have a single binary variable, then there's no reason to introduce complicated basis functions, because all these binary basis functions will also be binary. Okay. Well, we said so the number of parameters influences the overfitting and underfitting, the size of the data set, but also we can also, given if all these are fixed, we can also use regularization. So we can basically say that we want to minimize now the squared error plus some sort of norm of the regression weights, where the norm typically is a square norm. And if we do that and do it for different lambda values, then we also observe that as we increase lambda, the fit overfitting goes away, but at some point also we get some underfitting and the functions. Because in this case, all the regression weights get basically pushed to 0 because we penalize too much. Yeah, and this is also basically reflected in if we look at the actual regression weights that we get. And here, all of them go to 0. And well, we can plot the training and test error again as a function of this regularization parameter, and we see exactly the same picture as before. Yeah?
Yeah, I just have a point for everyone. But oftentimes when you're regularizing, you omit the first parameter of the y-intercept. So you don't want to penalize that because that's not really adding to the complexity of the model. So.
Yes, I mean, there's a way to avoid penalizing that, and that is if you first zero mean your y and all the x's or the phi of x's, you make a note of the mean of y, so you keep that, and then apply all of this, and you can basically use this mean of y later as an additional predictor, as a bias term, and that would be then not be regularized. In case you don't want to regularize it. Yeah. Okay, so I mean the picture is the same. We have regions where there's overfitting and we have regions where there's underfitting. We talked about the concept of bias invariance, where bias is basically the bias of a parameter or a function is the expected difference, where the expectation is over the data distribution between the true and the true parameter and the estimate, and the variance is just the variance of the estimate. So it's the expected difference between expected squared difference between its estimate and the expectation of the estimate. And we also said that there is that this parameter lambda affects bias invariance. So if we choose lambda to be very high, then we get a large bias. So this is the mean of all of these 100 learned regressors. We see that there's a huge difference between this mean, which is an estimate of the expectation, and the true. And the variance is very small, while if we decrease this parameter lambda, then well, the bias gets smaller, but also the variance gets larger, and the limit of making this lambda 0, then we will get 0 bias at some point, and the variance will be immense. I have to use my. Okay. It started to hurt, yeah. I think it will be bubbly. I just managed to pour a whole cup of miso soup over my hand. It was boiling hot, this one. I mean, it was really. So basically, what happened is, I had this cup. I wanted to open the lid. I opened the lid and I squished it a bit, such that only a bit went on my hand. But then this hurt so much that I kind of did some weird thing. I was it became disastrous. So and I knew it would become even worse, but there was nothing I can do. Okay. Okay, so lambda influences bias invariance, yeah, the bias invariance are basically the mean squared error can be written in terms of bias variance, where it is the bias squared plus the variance plus something that we cannot learn, which is random noise. And well, if we look at it empirically, then we see the same thing. So if we just compute empirical bias and variance, so this is the variance that goes down with larger values of lambda. The bias goes, the variance goes down with larger values of lambda. The bias goes up with larger values of lambda. And if I take the squared bias plus the variance, then this tracks very well the test error on a different data set, except for difference here, which we said is the noise. And well, I mean, this regularization framework is not just limited to a squared regularization, but you can think of anything. I mean, it doesn't even have to be written in that way. It's just some function, but if you write it like that, if you penalize the norm, then it gets a very, that's usually a very intuitive sort of regularization. And we said that if we increase this exponent here, then the function becomes more convex, so to say. And if we decrease it, then it becomes less and less convex until it actually becomes non-convex, smaller than 1. Problem is also there's a point where it becomes non-differentiable, which makes it hard to optimize if you use a numerical optimizer or so. Then we have to find tricks to get rid of this non-differentiability. And once we are in the regime where it's non-convex, then we even have to deal with local optima.
Can you explain these graphs a little bit more? What is it exactly and what are the axes?
Okay, so the axes are basically two betas,
Okay.
beta 1, beta 2. And well, this is 0. And now what these are kind of level sets of the penalizer. So wherever there's a green line, it means that the penalizer has the same value. So you give the same penalty for, well, say this is 1. You get the same penalty here. If this is 1 and this is 0, then if you put both of them to 0.5. Or here, you give the same penalty where this is 1, this is 0, to both of them being square root of 2. And, yeah?
So, for like 0.5 versus...
Oh, sorry, the penalty is, penalty is larger, sorry, yeah. Yeah.
So for like 0.5 versus 4, so when you have q equals 0.5,
Yeah.
That sort of structure will make your, it will favor one beta or the other, right?
Right, I will basically say this will favor solutions where as many betas as possible are close to 0 or at 0.
Yeah,
I mean, there's also the extreme, which is the so-called 0 norm, which is not really a norm, which is basically this to the 0, but which will only allow, basically, you just count the number of non-zeros in that case.
Yeah. Okay. And then going the other direction, it favors solutions that have large.
Yes, I mean, basically here it favors a solution where everything is non-zero. But I mean, typically people don't use anything larger than 2
So
in
what's
practice.
like the virtue of selecting one over the other? Why would you favor sparsity or not?
I think this is prior knowledge about your problem. I mean, if you think that your problem is sparse, so if you think that your data, I mean, you have only a couple of features that are actually relevant, then you want something that gives you sparsity, like a Q of 1 or less. And while otherwise, yeah, you might want something that is dense. I mean, kind of sparsity kind of does a feature selection because of this, right? Because of this property, because it sets weights to 0. Yeah. And well, this explains intuitively why this is the case, because if we compare like the level sets of the squared error with those of the regularizer, and we see that for larger Q, they typically meet somewhere off the axis, where once they are for these sparse regularization methods, they often meet on the axis. So the optimal solutions are usually for Elasto, the optimal solutions usually lie somewhere on this sort of diamond on the axis, which makes it really hard to optimize, because these non-differential differentiable points often contain the solution. Or almost exclusively, actually. Except you have like only 2 features or so, then usually they're both on. But if you have start with 1 million and run a lasso, then probably your solution will have a couple of hundred, a couple of thousand only non-zeros. Okay, so well, even more general, we said we can basically plug in any kind of function here as a regularizer, any kind of function here as the loss. Typically we use, we specify them in a way that both of these are convex, such that we can easily optimize them. And we also said that a lot of machine learning methods can be kind of explained in this framework, like support vector machines, the lasso, or whatever. Well, inference is done by minimizing this cost function. Either we can do that in closed form, like the loss is quadratic and the regularizer is quadratic, then we can just solve for it, right? Solving a least squares problem. That's what we also did by maximum likelihood inference. Or we use some numerical method.
Question.
Yeah.
What do you mean by hinge loss?
Okay, a hinge loss is basically a loss that. So support vector machines look at classification. So the output is 0 or 1, right? Now you could, I know you could either predict a 0 or 1, and you can basically, in the extreme case, do the 0-1 loss, where you say, if I predict a 0 and it is a 0, then my loss is 0. If I predict a 0 and it's 1, then my loss is a 1, and so on. So you basically just count the number of mismatches. But what the hinge loss does, it basically, instead of counting the mismatch, it basically does, if you have a classifier, kind of, the loss is 0 if you predict something larger than 1, or larger than 1, or smaller than 0, and otherwise it goes linearly, and then it levels off at 1. That's the hinge loss. The hinge loss basically looks like this. So it's kind of goes from 0 to 1. So that's the hinge loss, and then you sum it up over all of these. And it turns out that if you optimize this hinge loss, you basically get this property of getting a linear function that maximizes the margin in the support vector machine. Okay, so the question is now how to determine loss functions, regularizers. Say we have already a loss function because we're doing regression, so we typically use a quadratic loss function. Note an interesting thing is that you could also use, for example, an L1 loss function. Can you think of what this would do? Think of this picture again. What happens if we make this function here in L1?
You could have an infinite number of solutions. You could have an infinite number of solutions.
No. You also get sparsity in a certain way, but it's now a different sort of sparsity. So basically, what it will try is well, it's basically you have a loss. That's just. Lose the chalks, yeah. I'll just place one here, one here. Okay, so if you compare those loss functions, well, that's the quadratic loss of this. It's like that. look at the L1 loss, it's like that, which means that, right? That the L2 loss is small unless you're, for all of them, kind of in that region. For all the training data points, your prediction for all the training data points is all that in the region, and the L1 loss will now create sparsity in the sense that it will predict some samples perfectly, while others, where it doesn't predict well, because it only then the error only grows linearly versus quadratically. For some that it cannot predict well, it's fine. It doesn't care about them in effect, because it's basically this kind of O of n difference there, or O of the regression error difference. And the effect of that is basically that it's a little bit more robust to outliers. So say you have some samples that are you cannot really fit the regression function to. If you say that is your function. This is the data that I observe plus this one, right? Then probably an L1 loss would give you something close to here, whereas an L2 loss would try to fit something here and will move away. So it's basically robustness to outliers like this one to get. The problem again is L1 is harder to fit than L2. And yeah.
Do people ever use like L 1.1 because it's slightly easier, or is it still not any better because you have to take the absolute value anyway in terms of being differentiable?
I've never seen it. Is it non-differentiable, the L 1.1?
Well, because you'd still have to take the absolute value because you can't take the 1/10 power of a negative number without getting a complex value.
Mm-hmm. I would have to plot it. I don't know. So, yeah. Interesting question. I mean, what people also do pretty frequently is that, for example, they would say we use a loss function that looks like that, or a regularizer that looks like that, where you have basically a quadratic close to here, or close to here, say, and then at some point you keep on going linear. Then you've gotten rid of this non-differentiability, and but you're still robust to outliers. So it's basically in this case your loss function is not, you cannot write it as like that as a norm, but it's kind of an if then else. So if you're in that regime, it's a quadratic. If you're in that regime, it becomes linear. But it is differentiable, obviously, right? And that is what people use in robust regression. It's the Huber estimator. If you might have heard about that. If not, then you've right now heard about it. Yeah, so you can play around a lot with these sort of loss functions and regularizers and all of these things, and they will all give you a little bit a different solution with different properties, but all of that is kind of prior knowledge about your data, right? Okay, so the question is now, how can we choose a given regularizer? Or, I mean, also part of the regularizer, it's not just Q, it's also this lambda. I mean, how do we choose lambda given that we want to do a rich regression? Because a too small lambda will give us overfitting, a too large lambda will give us underfitting. But how do we know whether we have over or underfitting? And the idea is to use cross-validation. So when you want to minimize kind of your expected loss, but the expected loss is over, the expectation is over the data distribution, which you don't know. But you can kind of try to approximate this expectation using out-of-sample prediction. And the idea here is that you split your data in k sets of equal size. Say k is 10. And for each of those, in this case it's 3 on this example. And then for each of those, we call one set the test set, and all the remaining data the training set. Now we train on the training data, and then we use that regression function to predict on the test data that we have not used for training. And we do that for each of those folds, and then we average. And that kind of gives us an approximation to this expected loss. And, well, we would pick the model, where the model is now, for example, the lambda value that gives us the lowest average loss. And, well, because we, in the end, want to ideally use all the data, because data is pretty valuable. If you don't drown in data like Google or so, you want to use typically all the data. So you retrain given that model form, so given that lambda, on all the data. Right. So the funny thing is now, this is just a little question here. So how would you say you want to compare two models, but not taking into account their lambda value? So say you have a lasso regression and an L2 regression, and you want to see what's better on your data for their optimal lambda value, each of them. What would you do using this cross-validation framework? Okay, so say I've got two types of different models. Lasso regression, so an L1 regularizer and an L2 regularizer. I want to apply it to the same data set, and I want to compare them. I want to know which gives me the lowest expected loss, but not conditioned on a single lambda, but just give for the kind of optimal lambda. Yes, but what's the problem?
They have different loss. No, they have different measures of the loss.
No, the loss is the loss of the data. That's not without the regularizer. You don't include the regularizer in the loss here. So this loss is only the mean squared error in this case. You use the regularizer only when you train your model, when you learn your parameters. When you evaluate on the test data, you take the loss into account. Well, what happens if you? The problem if one does what you just said, and just for each of those run a cross-validation, giving me their optimal lambda value and this root mean squared error from over the cross-validated folds, then there is still you're basically still training on the whole data. It doesn't give you an out-of-sample estimate because you now chose your lambda based on the whole data. You used the whole data to choose your lambda. So what you would actually have to do is kind of a double loop cross-validation. For each of those training data sets, create an additional cross-validation over that training data set. Use that to get the lambda, predict on the test set, and then move on. So it's a double for loop that you have to do. On the training data, do another cross-validation, such that you never use your test set in order to evaluate the quality of your model. Yeah?
Are you saying you're splitting your training set into two?
Not into two, again into k folds. I basically I have an inner view where I view this training data set as if it was my whole data set. And I repeat the whole process on that for each of those. Then I get in the end, if I do that, if I'm done with that, predict that test set. If I'm done with that, predict that test set, and so on and so forth. So it's now k times k folds, basically, for each method, then the final result will be independent of, basically will not have used the whole data to assess the quality.
What is
to
the
learn the
reason
parameter.
for not just using one fold instead of using that one in all k sets? Like, what is the advantage from using different test data and training data for different parameters?
Because there's
It
still
almost
now,
seems to me like it'd be more advantageous to use the same sets, but very differently.
well, you can use the same sets. You can keep the folds between the two, between the lasso and between the L2. You can use exactly the same splitting, right? I think that's something that is reasonable to use exactly the same splitting to get numbers that match up. So, I mean, except for if you repeat that process many times. I mean, you basically could think of do a k-fold cross-validation and repeat that 10 times again. Because, I mean, if you do a k-fold cross-validation, there's now a dependence on, like, because you randomly split your data, and this randomness also has an effect. I mean, it could influence your decision in the end. If you want to get rid of this, repeat k-fold cross-validation, and in each of those k-fold cross-validations, do another cross-validation over all the parameters that you still have to set by hand, or that you choose by a k-fold cross-validation. Because now the k-fold cross-validation kind of goes into your model fitting procedure, so there is still some overfitting if you only do it with a single loop. If you now go to what I'm telling you is, if you now say after you do the single loop cross-validation or a double loop cross-validation, then you go to a new data set, that there's still some overfitting going on. Oh, sorry, you cannot actually go, no, you cannot actually, because you have now for each of those k-fold cross-validation, you have a different lambda, you can actually not, you don't get a single lambda of those. No. But your expected loss is still underestimated if you do that, because you use the whole data set. Because you still, I mean, there's still a maximization step. Because you pick the model with the lowest average loss, and that's the number that you report. And you don't want to, and every maximization step gives you overfitting. Because you fit something to the data in that by choosing the lambda with the lowest average loss. And if you want to get rid of this, you just put it into one additional layer of cross-validation. Okay, so well, we can interpret this sort of.
Sorry, I have one more question.
Yeah.
I'm going back. So once you decide the perfect model, you're going to retrain on everything, including the test data, right?
Yes.
Okay.
Yeah. I mean, this is in order to get kind of to quantify the expected loss that you have. Okay, so, well, so far we talked about some functions, some error functions and some regularizers that we optimize, but can we give this probabilistic interpretation? And of course we can, because, well, these squared errors, basically they appear in Gaussians, these squared, so basically, whenever we minimize a squared error, that is the same as minimizing or maximizing the log likelihood of a Gaussian. And the same here is true for the log prior distribution, if the log prior distribution is a Gaussian distribution. And the funny thing is now that this regularization parameter lambda now corresponds to the inverse of the variance in the prior. So basically setting lambda to 0 corresponds to letting the variance go to infinity of the prior, which means you can just do maximum likelihood. And yeah, and because we penalize the norm. That means that we're basically assuming that the mean of this distribution over the parameters is 0. Well, so regularized regression can be interpreted as maximum a posteriori estimation, because we take this function now, and if we maximize the log posterior, it's the same as minimizing the squared error plus the regularizer. And well, basically all these Q norms that we looked at before can be interpreted in terms of some exponential family, basically, distribution. For example, most notably the lasso, which corresponds to a Laplace distribution. If you take the Laplace distribution, it basically looks exactly like the Gaussian distribution in the exp, just that it takes an absolute value instead of a squared. So it's exactly like in the Q norm, where you take the sum over absolute values instead of the sum of squares. Okay, so let's go to Bayesian linear regression, where we don't do maximum a posteriori estimation, but do full Bayesian inference. We have the likelihood as before. We define a prior over the regression weights, right? That prior is Gaussian, has some prior mean and a prior covariance matrix. And now we want the posterior. The posterior is proportional to the product of the likelihood, where the likelihood is over all the n individual data points, times the prior. Can now rewrite the likelihood as a multivariate Gaussian, right? Again, here we have those basis functions in there of our axis, giving us basically a nonlinear, possibly nonlinear regressor. And well, if we take this product, then we can again, as before, solve for a distribution in beta. Here, this should actually be a proportional here. It's not no equal. But we know that the posterior is normalized. We know that that's the conjugate prior, because it's the mean of a Gaussian again. So the kind of the normal distributed regression weights are conjugate prior to the regression weights in a Bayesian linear regression. We can write the posterior distribution over the parameters with some posterior mean and some posterior variance. And the posterior mean, it turns out that this is equal to the posterior covariance times some weighted mean of the of y, weighted average of the prior mean times the inverse prior covariance, and kind of the correlation between our inputs and the y. And the prior covariance is now, or the inverse prior covariance is now basically the sum of the inverse posterior covariance is now the sum of the inverse prior covariance and the covariance, or the inner product between our inputs. So this gives us again some closed form solution. I mean, you should actually derive that at home.
It's basically the same thing as that formula for.
It looks completely analogous, and
yeah.
the way to achieve it is exactly, it's the same calculation. It's just you have different variables basically.
Yeah.
Yeah. And instead of just having the mean, you now have x times beta. Yeah, exactly. They look very, very analogous. And well, this is exactly what we said. And in order to go to rich regression, it corresponds to, say, sending the prior covariance to 1 over lambda times identity, so it's independent independent Gaussian on each of the entries of beta and mean zero normal distribution. And in this case, the posterior parameters simplify a little bit, and we just get we basically, because this part is 0, it goes away, and this part is now lambda times identity, so this will be exactly the ridge regression. The mean will exactly be the ridge regression estimate, and that is an exercise that I encourage you to do, to derive these two, to write down the squared loss plus the squared penalizer, and try to minimize that using linear algebra. Take the derivative or the gradient, set the gradient to 0, see what comes out of it, and again do the same process here for the posterior Bayesian estimate, where you use completing the squares in order to get them. And you will see that you get both, that both are the same. But the posterior mean is the same as the map estimate in this case, or the ridge regression estimate. And well, for lambda equals 0, this will be the same as the maximum likelihood estimate, which again corresponds to an improper prior because it has infinite variance. So a distribution with infinite, a Gaussian with infinite variance is basically a uniform distribution over the real line, something that you cannot normalize. That's why we would call it improper, because you cannot find a constant that you multiply to it such that it sums to 1, because it has mass everywhere. You cannot normalize it. But once you go to the posterior, it's actually proper. So then you can normalize it. Well, we said for the Gaussian distribution, we can come up with this kind of sequential learning. You can do the same thing here, and that is what I'll show you now, and that's actually quite funny. So we start in the beginning with our prior, right? Our prior is basically a spherical Gaussian 1 over lambda times identity. So you have, so you basically have just your level sets are just these circles around the origin, around 0, and well, because it's a Gaussian, we can now sample from it, right? So we can sample 2 weights, and if we sample these 2 weights, they give us a regression function, right? And if we take these samples, then they will look like these regression functions. Do you realize what it means to sample from this and then plot it like that? You basically you sample in some abscissa, or something that like a bias term, and how do you call it? Slope. Yeah, right. That was the word I was looking for. Sample a bias and a slope, and both of these are Gaussian distributed, and then you plot them by drawing a real line. Now we observe one data point. What happens if we observe one data point? Well, basically the data point actually was generated from the true beta, which is here, which is unknown, right? The true beta is here, and well, this data point is here. They are now, because we are fitting basically 2 parameters to this one data point, they're now, all these linear combinations would give you the same likelihood. So you can basically, if you, well, this is for example an example here. This line almost goes through this point as well as this, and turns out that if you plot the bias versus the slope, the likelihood as a function of the bias and the slope, you get this line, this sort of Gaussian. And so whenever you pick a set of beta 0 and beta 1 that lies here in the middle, it will give you the same likelihood for that one data point. Now, we take this distribution, in this distribution, we multiply them together, normalize it, then we get this distribution. This is our posterior.
Sorry, can you explain that far left one again? I did not catch the explanation.
Okay. So we only have one data point, but we have two parameters. We have a linear function of two parameters, which means that in order to perfectly explain it, we only would need one, right? So it's overdetermined right now, our equation system. If you view it as a linear equation system, you want to find a linear function that gives us, well, it's basically some linear combination of a plus b that equals our x that we just sampled.
Yeah.
You can say x is 1, then I can give you 1 and 0. I can give you 2 and minus 1. 3 and minus 2. They will all give you, if you add them up, the same value here. And basically, all of these solutions are basically correspond to these lines here. So this line, you can, so this is the trading data point. All the lines that would go through this point give us the highest possible likelihood.
Okay.
And if I plot the likelihood as a function of the two betas, I get this. And yeah, the lines would look like this. So it's
Okay. So why are we doing this?
why are we doing this? Because we want to learn the true function. We want to learn the true beta. So it's and we're doing we're using this conjugate idea in order to come up with the sequential learning, where we just update the posterior in each step. So the
Okay, so we're giving it one data point at a time.
yes,
Okay.
and then relearn the thing. So after one data point, this is our posterior.
Okay.
Now we add a second data point, and again, what we do now is basically we now use this as a prior. So our posterior from before becomes now our prior. We again have a likelihood. It's again a likelihood only consisting of one data point. So we again have this likelihood that looks like a line. And if you now multiply this likelihood with this prior, well, our old posterior is the prior, then we get this posterior, which is already much more peaked. And if we sample from it, basically sample from this posterior, then we only get these sorts of functions. Now we do that for 20 data points, and we've recovered the function. Does anybody have the time? Okay. Okay, so can we make predictions? So everybody has understood this now? This idea? Well, making predictions. So for, well, if we just have a single beta, then making a prediction is trivial, because so we get a new x that we haven't seen before. Well, the prediction, we know that the likelihood is Gaussian, so we just take that x, plug it into the basis function, and use this weight estimate beta in order to compute the mean of the distribution, and the variance is just the variance of the data, right? Well, but if we have in Bayesian inference, we don't have just a single estimate. We have a posterior distribution, and this posterior distribution has a variance. So it doesn't just have a mean; it has a whole variance. It's not a single point estimate. It's a distribution which has uncertainty. So what we want to do is we want to integrate basically our prediction for this new sample is now the integral over all the possible beta values over the posterior, which is the probability distribution of beta given our training data. And yeah, I mean, we said that this integral, so this is now the likelihood for the test data. It's just plugging that in. And now it's the integral over the posterior, where we just said, we just gave you the formulas of the mean and the covariance of that posterior. Well, how can we solve that? That's something that I won't go through today completely. I will encourage you to do it as a homework exercise. I put some Gaussian identities, a link to some Gaussian identities online that are quite helpful, if you want to solve these. But I show you some little tricks. So, well, if you have a Gaussian function, then really writing the Gaussian function in x beta, or with mean x beta, or in the variable y, is the same as writing it as the variable x beta with mean y. Because if you look at the quadratic, the part in the exponent, it's just right? Now, this is the variable that the distribution, and this is the mean. But if we flip those two, if we solve the square, it will be the same. So this is something that we can do. The other thing that we can do is we said that if we have a distribution in beta, then we know what the distribution of x beta is, because it's a linear transformation of a Gaussian distribution. So we can replace this Gaussian distribution with this Gaussian distribution. The difference will only be a constant. The funny thing is we don't care about constants here, because we know that in the end we will get a Gaussian distribution in y, so that will be normalized. We don't care about constants right now. That's why we have only proportionals here, because this is not equal to that, but it's equal times to that times a constant. But forget constants, we don't need them. And now, instead of integrating over beta, we integrate over x times beta, or phi of x times beta. Because, well, it's just this distribution. Now we have basically the product of two Gaussian distributions that they both are in x beta. And it turns out that we can now use some formula to look up what this product is and what the integral of the product is. It turns out this is actually, the whole thing is actually a Gaussian convolution here. And then we get a prediction, which is basically the predictive distribution will have phi of x times the posterior mean of beta. And the covariance will be, well, sigma squared times identity, that's missing here, times plus some additional covariance. So one interesting observation is that the variance of the predictive distribution is larger than the variance of the likelihood. So the variance goes up because there's additional uncertainty about the mean. And I think you want to make a short pause, so do a short pause. Okay, so, well, in the predictive distribution, we said that, well, this was just the variance that we derived on the page before. But, I mean, the marginal of this for a given individual is just the variance of just the noise variance plus plus the variance that comes through the posterior. Well, the linear transformation of the posterior times x. So this is the posterior covariance of beta, and this is the linear transformation of it. And the covariance between 2 points, between 2x, so between one x and another x, is now, well, because this part is identity times sigma squared, there's no noise variance, so it's only the covariance only comes in through this here. So it's basically, so it's phi of x transpose times Sn times phi of x prime, where x prime is the second point. And, well, if we now fit 9 basis functions, then we can evaluate the predictive distribution. So this is our training data point. And, well, for every point, this is the function that we learned. So this is our mean. And, well, the mean is pretty boring because we only had one observation. So it's just some function that goes through this point. What we observe is that basically for every point we can now get the variance. So we can visualize it by plotting basically the region of plus minus 2 standard deviations. Right? From the variance we can get the standard deviation. So we can basically shade everything that is shaded is the mean plus minus 2 standard deviation. So it's a 95% confidence interval basically of a Gaussian. So 95% of the mass of the predictive distribution is within those shaded areas. But of course, we can only, because we basically what we do is we just plot the function by evaluating it many times, right? For every point on x, we evaluate the function and we evaluate the marginal variance. But it doesn't tell us anything about the covariance. What do we understand with it? What do we mean if we say covariance? Basically, how, so if I give you 2 x's, how does the function that we have learned covary between these 2 points? So if a function covaries a lot, so that means that y is pretty much the same. So if the function covaries, so a covariance between, it's basically covariance between function values. If I change one function value, the other one will change in the same way. So it means that if there's large covariance between 2x of the function values of 2x, that they go up and down together. That's what the large covariance means. And small covariance means that knowing one function value tells you nothing about the other function value. And, well, we see that the variances are pretty large, and also how can we evaluate the covariance? Well, there's no, or how can we plot it? There's no easy way. The easiest way is just to sample many functions from our posterior. Right? We have a posterior distribution of the betas, so we just get samples from the posterior. It's a Gaussian distribution, so we can, for every basis function, we can get a beta. And plot these functions. And this kind of tells us how, for 2 x points, these function values covary. And what we observe is that, well, the function wiggles a lot, so there's not much covariance anywhere. But most of these, because of the small variance, it means that all the functions will be, at this point, it will mean that all the functions will try to go through, to be close to this point. Now we get a second point, and we see that in this region, the variance goes down. Right? And if you look at the covariance, then also the covariance becomes larger in this region because there's not as much wiggle anymore.
Is green the underlying distribution?
Green is the true function that is distorted by noise. Basically, blue are samples from the green function plus noise.
Okay.
Now, we get more data points, and we see that wherever in regions where there are many data points, the predicted variance. So basically, if we had a new data point that would lie here, then we predict this mean, the red function as the mean, and this kind of variance for it. That's what it means. It means that if we observed a new x here, we would assume that its y value would be in this region, kind of, and most likely on the red line.
Question.
Yeah.
Is it just coincidence that most of the on the right, most of the lines go up and then down, or?
No, that's a complete coincidence. Yes.
Okay.
Because if you look at this, I mean, they could basically go up again. It's just actually
Mostly.
the wiggliness of the function depends on the number of basis functions used. If you use fewer basis functions, so here we use 9. If you use 100, you can get functions that go like this. Because you get and they go up and down because you get these huge weights and whatever, right? Well, and then for many points, the variance goes down everywhere, and the mean also tracks the true function very well, and the function. If you look at covariances, basically, how does the function value here and here covary? Well, the covariance is pretty determined here. So variance approaches the noise variance for large sample sizes. So, well, basically this is only now the shaded area just is sigma squared in the end, and the covariance between close x values is high. Whereas the covariance between this x value and this x value is probably not very high. Well, actually, because the function is determined every way, there is covariance, right? I mean, it's if you because you know that there's kind of a sinus in between. You know the function that is between these 2 points, so there is covariance.
So between all the points there's a high covariance?
Well, I would guess that the covariance between this and this would be negative, right? Between this and this, because the y value of this is always smaller than that, so you have a negative covariance. Okay, so that was Bayesian linear regression. The question is now, how can we use that for model comparison? And if we have ways to compare models, then this also means we can test models if we can compare them in some way. So, well, why do we want to do model comparison? It's the same question. I mean, we have been studying model comparison before when we went to cross-validation, but this is now kind of the Bayesian way to do cross-validation. Is not the better way. It's a little bit cheaper actually than cross-validation, because the cross-validation needs all these like for loops, right? And it's really expensive. You have to train your model many times, and we'll see a way to use by using Bayesian inference to just get kind of an approximation to what we had before. So, what is the degree of polynomial that describes the data best? Well, do we have at all the correct model? Or should we use something else? Or, well, does a SNP have an effect on the phenotype? That's all the types of questions that we can ask if we do model comparison. Well, say we have a bunch of models, H0 to Hm, and a data set D. For each of those models, we can now compute the posterior probability of that model by, well, computing kind of not the likelihood of the data. It's not, so because the model has parameters, this is kind of the, under the model, the probability of the data. So it's the, if you remember Bayes' theorem, what you said before, you have P of P of beta, the parameter given the data, equals P of data given beta times the prior over beta over P of the data. Well, it's the integral, basically, data given beta. But what this really is kind of, I mean, we're kind of saying that we already specified our model here, right? I mean, we already have, our model already contains these betas. So what we can write it a little bit differently, say, well, it's kind of, this is, we call this H0. We have then basically this here is, well, we said that this is P of the data. Instead of calling it P of the data, so it's now the P of data given H0. So it's the normalization constant in Bayes' theorem that we consider here, and that is what we call the evidence. Say say H0 is a model with 2 basis functions, and H1 is a model with 10 basis functions. Right?
What's the difference between likelihood and evidence?
Well, the evidence is the marginal likelihood. It's the taking the well, this is the likelihood, but marginalizing it over all the, sorry, this is also times P of beta given H0. So it's the integral over the likelihood times the prior. That's the evidence. Which again gives us something that we could interpret as a new likelihood. That's exactly what we do here, where all the parameters have been integrated out. It's a likelihood that doesn't contain the model parameters anymore. So it's basically if H0 is the model with the 2 basis functions, then it's the, well, how do we explain our data with 2 basis functions if we take all the possible parameters under a prior into account? That's what the evidence tells us. And so it's again kind of a likelihood, but not the likelihood as before, but one level above. So we're now doing Bayesian inference instead of on parameters, on models. So it's one going from parameters, one step up. Before we always conditioned on a single model. Here we have multiple models that we compare. Is the concept clear? Yeah? Okay. That's exactly what I said. So the evidence is not the model likelihood. So the evidence is exactly this integral over all the parameters the likelihood times the prior. And, well, this is, I just repeated on the slide exactly what I wrote on the board. So that the posterior of the parameters given the data and the model class is the likelihood times the prior over the evidence. So we use this evidence now, which we also call marginal likelihood.
So, do we have to worry about how to compute that? Like, is that
Yes, we do have to worry about how to compute that, yes. But the nice thing is that for Gaussian likelihood and a Gaussian prior, it comes out you can write it down in closed form. Using this Gaussian convolution. It's basically, what it basically is the predictive distribution evaluated on your training data, or on the whole data. That's what the marginal likelihood is. Because you have your posterior estimate kind of, and now you're integrating over, let's see, the probability of your data times the parameter, given the parameter, integrated over the prior. So it's exactly the predictive distribution for your training data. Evaluated on your data. So the interesting thing is that the evidence penalizes two complex models. Say we have two models where one model, so this is now a model conditioned on a given parameter. But for this parameter, because it has, say, H2 has 9 basis functions, H1 has 2 basis functions, then probably if we maximize, if we find the best possible parameter such that the likelihood is maximized, the likelihood of the function is maximized, H2 might get a very high likelihood on our particular data set. But if you go to a different data set with this parameter, it will probably not perform very well. Where H1 might not perform that well on one data set, but might be more robust. So if we then say kind of average the likelihood over all possible parameters, before we only looked at one parameter, then more complex models will basically have a low fit for most of the times, and this will result in a lot of evidence. Because, I mean, so if you have a very complex models, you can find some parameter that some parameterization that it will fit very well on one data set, and on another data set, and yet on another data set. But if you have a very simple model, well, you cannot choose your parameters that much. So it will only fit a certain kind of data sets. But we know that if we integrate over all the data sets, this integral has to be 1. So if you have a very complex model that you can fit to many data sets, that has basically, you have to normalize this integral such that it is 1. So, well, the evidence gets very small. While if you have a very simple model, where basically you have a very small, where you have a very bad fit to a lot of data sets, but it fits a couple of data sets very well, and you integrate that, actually the evidence might be high. And say we observe a particular data set, then this means basically that we want the lowest complexity model kind of that still explains our data set very well. And that is kind of what people denote as Bayesian Occam's razor. Do you know who Occam is? Occam is this was I think a monk who basically said, well, if you have many hypotheses that explain my observations, then give me the simplest one, because the other ones probably won't hold. The more assumptions you have to make, the less likely it is that actually your hypothesis will hold. And if you use the evidence, it will automatically penalize complex models. Yeah.
it's saying that it says complex models have low average over many possible data sets, whereas simple models have large evidence on a small range of data sets.
Yes.
I thought, wouldn't it be the opposite? Wouldn't you have complex models that fit certain data sets very well and then not well on the others?
No, I mean, you can basically now change the parameters. You see a new data set, oh, then you just go to another space of the parameters.
Okay.
But once you integrate over all possible parameters, so basically if you take the average over all possible parameters, then for most of the parameterizations, the fit will be very bad to this data set. Because you have so many combinations, most of them will be complete crap.
Okay. So
But a couple of them will be very good. But you have to average over all, so the average goes down.
okay, so integrating over your data sets for evidence is different than integrating over the parameters, which is what, on the last slide, were we showing integration over parameters? It seemed like the last slide had a slightly different.
Well, I mean, the last slide was, that was basically now if you could choose your parameters such that you get a good fit.
Yeah.
So,
So those are parameters?
yes.
Okay. That-
And it turns out if you do something like BIC, you know what BIC is? BIC can basically be viewed as, so we basically have the likelihood plus some log penalization for the number of parameters. You can derive, it's a Bayesian information criterion, it's actually an approximation to the evidence. It's a very crude approximation, but it is an approximation. It basically does a Laplace approximation and then drops a bunch of terms and then you get to BIC.
Can you repeat all of that? I'm sorry, I didn't.
Okay, so you basically start with the evidence, you do a Laplace approximation to the evidence, which basically means you do a quadratic expansion around the max, right? And by a Taylor series expansion, too. And then you drop a bunch of terms of that, because it's still too complicated. Then you get BIC, the Bayesian information criterion, that many people do to compare models. So let's try to apply that to GWAS. Well, say our assumption, or our null model is, well, there's no association. So we just have a model, has zero mean, or say it's a constant mean, or that these are zero means, so then we don't need the bias term. It's zero mean, and now our model is only sigma squared, so we have that's our prior here. Where our alternative model is there is an association to a SNP, then we can basically compare that model to a model that has a linear function in that SNP. And now we have a more complex model because it has two parameters, and we have to integrate over the two parameters. And now if basically, because of this kind of Occam's razor effect, if actually there is no true association, so if X has no effect on Y, then most likely the evidence will go down, because we have to integrate over all the possible ways of beta, we have to average, and the integral has to go to 1, so that will be bad. Well, and depending on the choice of priors, the required integrals will be tractable. So in this case, the priors have to be conjugate, and again, we have the mean and the variance of the Gaussian that we're parameterizing here. And it turns out that this will basically be a Gauss inverse gamma prior again. So, well, how can we now score something? Well, we can do something that is absolutely analogous to a likelihood ratio, where before we just took the likelihoods and wrote the ratio of those, or the log of that. But in this case, we take the log of the two evidences of the two models, and that is what is called the Bayes factor. Note that for the likelihood, it was the case that the more complex model, so the one with the SNP, always achieved a larger likelihood. So this ratio was always larger than 1. In this case, because of this Occam's razor, actually it can go smaller than 1. So the log likelihood ratio can go both positive as well as negative. And well, we can then, for example, compute that for every SNP, and then we can plot the base factor for each SNP, and we get some basically a Manhattan plot, which is similar to the plot of the log p-values before. Now, well, base factors are very useful. The nice thing about this is, in a likelihood ratio test, we always needed the null model or the alternative model to be exactly like the null model plus some additional parameters. With a base factor, this doesn't have to be the case. We can basically, from the null model to the alternative, remove a parameter and add another parameter. That's something that you cannot do in a likelihood ratio test, but you can do it when you compute base factors. Well, okay, so can we use that base factor to compute a posterior probability of a model? So what is a posterior probability? Well, now the probability that a hypothesis holds given a data set is, well, exactly what we had before. It's the evidence times the prior over that hypothesis over the probability of the data set. What's the probability of the data set now? This normalization constant. It's the probability of the data. So it's the evidence times the prior over the model summed over all the possible hypotheses. So if you're comparing, yeah.
So I'm sorry, we're only saying that there's two hypotheses?
Yes, that's currently, you have the model without the SNP, the model with the SNP. I mean, you can even have more. If you have more models, then you just have a longer sum here. But what this means is that basically you can use Bayes' theorem to get a number between 0 and 1, which is the probability of your hypothesis. And that's, yeah.
So here we're determining the probability of the alternative hypothesis given the data. But what were we doing before? Isn't this a critical thing?
Before we were computing the evidence, which is the probability of the data given the hypothesis. So it's the kind of the reciprocal of the thing. And this is the probability of the hypothesis having, so of the model being true, or the true one, among our models that we consider, given the data set that we observe. And, well, this is the probability of the whole data. So the sum of that is 1. And the nice thing now is that we can now compute that, and it's basically now, this is a Bayesian posterior probability. If that is close to 1, then already, as long as this is larger than 0.5, it means that this model is more likely than the other model. And if it's close to 1, then it means that probably there's an association. So let's compare a bit Bayes factors and likelihood ratios. Well, Bayes factors have the big advantage that we can compare models with different complexity. These are, I mean, these tests come up, for example, in causal inference. If you condition on different variables, then sometimes the models are not completely nested. That all the parameters in the null model also appear in the alternative plus additional ones. it also enables us to actually test a simpler model, because we can say, well, actually my test that I want to do is, everybody says there is this variable of influence, but I say there's no. You cannot do that with a likelihood ratio, because you can only test a more complex model, while I say there's no influence, so I can just turn the thing around if I want to. Well, and the statistical significance is just a posterior probability of the model. Well, on the likelihood ratio, the number of parameters basically affects the likelihood ratio. So if you add more parameters, you will always get larger likelihood ratios. But the nice thing is that, so asymptotically for the large n case, for many samples, we know the null distribution because it's a chi-squared with n degrees of freedom, where n is the number of parameters in this case. Or d degrees of freedom, where d is the number of parameters, because n was the sample size. So we can compute p-values. We cannot compute the p-value for this. We don't know the distribution of these. But I mean, there are already probabilities. So we don't really need a p-value for them. They already, by itself, tell you something about statistical significance. It's just a different interpretation. The problem with these is, well, unless you do this like simple conjugate framework, they're often very hard to compute, while these are typically easy to compute. Yeah, let's look at the time. I think we should not start a new topic now. Any questions to this? No? I'm still around. Just to